What you are seeing is the modern data bottleneck, massive volumes of real-time information trying to squeeze through a chaotic web of point-to-point connections. Under these conditions, traditional transient message queues break down. They hit severe I/O limits and frequently lose data entirely if a server crashes under the load. To solve this gridlock, engineering teams turn to the architectural blueprint we are exploring today, outlined by Royal Research, Apache Kafka. Kafka operates as a distributed event streaming platform. Instead of the traditional fire and forget messaging model where data vanishes after it's read, Kafka centers its entire design around a persistent distributed log. To understand how it achieves its massive throughput and low latency, we have to strip the system down to its first principles. We are going to build a highly scalable, fault-tolerant Kafka architecture from the ground up, starting with a single data pipeline. Because handling millions of operations a second doesn't happen by accident. It is the direct result of deliberate, foundational structural choices. This single pipeline is a topic, the channel where data is published. Routing all events through one topic on a single machine hits a hard throughput ceiling. Kafka bypasses this limitation using partitions, dividing the single topic into multiple horizontal tracks to instantly clear the bottleneck. These partitions do not have to live on the same server. They can be distributed across entirely different physical machines in a network. Splitting the data stream this way allows multiple distinct consumer applications to read from the topic at the exact same time. This parallelization is the core engine behind Kafka's ability to ingest millions of events every single second. But dividing the pipe introduces a strict engineering problem. If related data is scattered across multiple different tracks, how do we guarantee it arrives in the correct chronological order? Partitions successfully transform a sequential bottleneck into a scalable highway, but they require a precise routing mechanism to maintain data integrity. That mechanism starts with producers, applications publishing data. Here, a producer labels a data block with a distinct tag, a key. Approaching the partitions, a mathematical hashing function analyzes the key and routes it exclusively to a specific destination, like partition 1. Kafka uses this key to deterministically govern routing. Any future message carrying that exact same key will automatically and flawlessly be routed into that exact same partition. Now we look at the other side of the equation, the consumers, the applications extracting data out of Kafka. A consumer reads a partition sequentially, processing the events exactly in the order they were appended to the track. Because the key forces all related events into one single partition, the consumer is mathematically guaranteed to read them in the correct chronological order. As Royal Research notes, by pairing keys with partitions, Kafka achieves massive concurrent processing without sacrificing the strict data integrity required by complex applications. To see how this logical structure survives the real world, we zoom out to the physical hardware. These server towers are called brokers, and they are the machines that actually store the partition data. A simple broker is highly efficient, capable of handling thousands of partitions simultaneously. When multiple brokers work together over a network, they form what is known as a Kafka cluster. Within this cluster, Kafka uses replication to eliminate single points of failure. Partition 1 resides on the first broker, while duplicate copies are maintained on the others. Managing this redundancy requires an overarching control node, traditionally handled by Zookeeper. Zookeeper acts as the coordination layer, constantly tracking the health of every broker and ensuring the system remains consistent. Which brings us to the ultimate engineering test, hardware failure. If a broker abruptly crashes and drops offline, its connections are severed. Zookeeper detects the failure instantly, rerouting all incoming producer and consumer traffic away from the dead server, directly to the replicated copies. Decoupling data storage across a clustered architecture and managing it with a smart coordinator guarantees high availability and zero data loss for mission-critical systems. There is one final flaw in traditional message queues that Kafka resolves. Legacy systems typically delete a message the moment it is read. Looking inside a partition, we see how Kafka manages memory. It writes every event durably to the server's hard disk. This creates an immutable, append-only log. Once data is written to this log, it cannot be altered. Consumers track their exact position in this log using a pointer called an offset, advancing step by step as they read. This disk-level durability enables replayability. If an application crashes, you simply rewind the offset pointer to read historical data. This capability forms the foundation for the architectural pattern known as event sourcing. Instead of simply overwriting a database table with current values, event sourcing stores every single state change as a reliable, immutable sequence of events. Because the log is persistent, Kafka effortlessly serves up real-time data streams and historical batch processing simultaneously. Dedicated tools like Kafka Streams and KSQL DB run directly on top of this log, allowing applications to compute continuous, real-time insights as the data arrives. Disk durability bridges the gap between historical data integrity and real-time processing, providing a permanent record of every event. Looking at the fully assembled architecture, we have producers and consumers interacting with a partitioned, distributed, and disk-backed event log. To bridge this core with the outside world, developers use Kafka Connect, facilitating seamless data integration with external databases and legacy systems without writing custom code. This completed architecture allows organizations to synchronize data across disparate systems in real time. These distinct data streams flowing into a central core show the mechanics that power continuous IoT analytics and instantaneous fraud detection. Its specific design makes it equally powerful for heavy-duty log aggregation as it is for complex, low-latency, event-driven applications. This aligns with the core thesis from Royal Research that understanding the platform's internal architecture is necessary to utilize its specific strengths. By scaling via partitions, securing via clusters, and persisting via logs, engineers can eliminate data gridlock and build the highly available systems that modern business demands.